So let's begin. I sent you a one-slide PowerPoint that was essentially the answer to the Van Hoff problem, the radial distance and how you solve the problem. So some of you, sometimes all of you, but some of you have been having issues with solving some of these problems. It's pretty clear that part of the problem is algebra. You don't know how to manipulate stuff, so you're out of practice. Some of the problem is differentiation. And so you've forgotten some rules. I sent you a link to a website that basically has reviews of math concepts. I'm not exactly sure what the overall goal of that website is, but they have a massive amount of review stuff. I think that guy collaborates with the Khan Academy people, and part of their interest is graphical representation of math concepts. But in any event, if you were to look at some of those videos, you would revisit stuff like the power law and how you differentiate x to the n and things like the chain rule and etc. That's sort of what he's doing there. It has the flavor, if you've ever watched Khan Academy videos, it has the flavor of Khan Academy. But it's a little more advanced than Khan Academy, I think. So that might also be useful. But in any event, I'll continue to make short slide introductions to concepts when you have problems with them. You can use those in redoing some of the questions that you mess up on. As I say throughout this course, our goal is to teach you some basic concepts about thermodynamics, binding, biophysics, biophysical methods. I don't necessarily expect you to be an SS expert, but I'm not backing down from teaching you at a higher level. And so I'm sort of laying a gauntlet down, and you're just going to have to put up with me. So I haven't shared my screen yet, have I? No. We finished last time here. Can you see these figures over here? Are these in your way too? Yes?
Yes. Yes.
Okay. And that's in the way too. We finished last time with this Van Hoff relationship, which is basically taking the relationship between free energy and enthalpy minus T delta S and relating that to the definition of the standard state free energy as minus RT ln K. And so combining these two equations into a linear form that when you plot ln K versus 1 over T, you get a slope that gives you the enthalpy, and you get an intercept that gives you the entropy of the reaction. I'm indicating here that I think there's a mistake in the book. And the point here is that if you can make a measurement somehow, we haven't yet talked about measuring equilibrium constants. We're about to, and we're about to do a lot more in the next 3 weeks or so. But if you plot ln K as a function of temperature, so you make measurements as a function of temperature, Often what you will get is a straight line, and the slope will give you this enthalpy estimate. So this will be known as a Van Hoff enthalpy. It is true that if you get a straight line, then this is probably a two-state process. There's nothing more complicated going on. It is probable that the enthalpy is not temperature dependent. The enthalpy can be temperature dependent, and in fact, it often is temperature dependent. We'll talk about that in some detail. And so this is one way of getting enthalpy. As I say, we call this the Van Hoff enthalpy. This chapter in this version of the book, when they went to multiple authors, when Ken went to multiple authors on his textbook, added a method section to this chapter. And the method section covered calorimetry because at this point, calorimetry measures the amount of heat which can be equated to the enthalpy at constant volume or constant pressure, depending upon the method. And so it was introducing experimentally the idea that there's another way of getting the enthalpy, another way that is more sensitive to things like not being two-state and having a temperature-dependent enthalpy, which also means you have a temperature-dependent entropy. And this chapter covers two techniques, one of which is DSC, differential scanning calorimetry, which is generally used for phase changes. In other words, protein denaturation, or literally a phase change when something changes state. I have used it, people are using it to measure condensation reactions. And then the other method is something called ITC, which we'll cover second, and that's isothermal titration calorimetry. And that's usually for mixing, is the way it's described in this beginning section, or a titration experiment, where you're actually measuring the heat evolved upon binding of a ligand, for example, to a macromolecule, for example. So it begins by saying that bomb calorimeters, which is basically a closed device and constant volume, can be used to measure the heat of denaturation, the heat of unfolding. It can be used to measure the heat of degradation. You can actually blow molecules apart and measure how much heat is evolved. That's not usually what biochemists use or biophysicists use. It's more of a chemistry sort of use or a physics sort of use. In chemical reactions, biochemical reactions, we usually use a device demonstrated on the right in that picture that is under constant pressure. And you basically put it under constant pressure so that it won't evolve bubbles, because bubbles ruin the whole thing. You're measuring the heat evolved in a very specific volume. Some of the bomb calorimeters have sort of a lollipop structure. Well, it's right here. It has a lollipop structure like this, where there's a device at the bottom that you fill. One side is filled with reference, which would be buffer in our case, and the other side is filled with macromolecule. Some of the calorimeters, it's not a lollipop like this where there's a filling device at the bottom. It's a spiral that has a filling at both ends, and the spiral is sort of in the middle, and there's a spiral for the buffer and a spiral for the sample. And then you heat the sample as a function of temperature, and you measure the difference in heat between the reference and the sample. Basically, the measurement is done electronically. You're basically trying to maintain a constant temperature between the samples. And how much current it takes to do that is a measure of the amount of heat that's coming either out of the sample or going into the sample. As I point out over here, it's heat absorbed or heat released. And so it's measuring what is called the excess heat during this temperature rise. And this is generally what the data looks like. If you then go and do the buffer on buffer, it also tends to have a curve, although it tends to be flat. And then when you subtract one from the other, you tend to get something that looks like this. This is an idealized picture. Okay. And so this gives you a calorimetric heat. In this case, it's probably describing the melting of a protein. Okay, and the evolution from a native state down here to a denatured state at the top. That's on the next slide. And what you end up doing is getting the amount of heat as measured by a heat capacity times the temperature change, and that ends up coming back to you as a ratio. And it can give you the heat, but that then is equatable to the enthalpy at constant pressure, as we've shown in previous slides here and in the previous text. Okay, and so that's generally the picture of what's going on in a typical differential scanning calorimeter. I will tell you that this device with a lollipop design, we used to have one of these here in biochemistry. We used to have a couple of these in biochemistry when other people were still on faculty. The one that we had, we gave to Mississippi State. And so Joe Emerson now has this instrument up at Mississippi State. The spiral design, Reed Bishop has one over at Belhaven. And that's the one that if I do something with it, that's the one that I use. So the transition is depicted here in more detail, in a more realistic depiction, because it turns out that the heat capacity for the folded state and the denatured state are not necessarily the same. And so you can get this change in enthalpy over some temperature range where you're basically integrating between T1 and T2. And there's a heat capacity dt, but the heat capacity need not be constant. The enthalpy need not be constant, okay? And so what ends up happening is you get these weird baseline effects. And there's sort of a break where initially you've got native state, and then it denatures somewhere near the peak completely, although at the peak, it's usually a 1-to-1 ratio, an equal amount of native and denatured. And then it goes into the denatured state. And so the baseline is the native state versus the denatured state baseline, or the heat capacity. And you sort of have to fit for that. You sort of have to get an estimate of what that looks like. Often there's this funny break or a gradual break, and you have to figure out how to account for that. That is sort of the main art form of fitting calorimetry data. But in any event, you end up getting total heat, you get a temperature of melting or denaturation, and you get information about the enthalpy change in denaturation, okay, as depicted in this slide. Okay. The thing about this is that at every point across that curve, okay, there's some kind of a transition from a native to a denatured state. It's really only at the peak where you tend to have equal concentrations of native and denatured. At that point, the equilibrium constant's approximately 1. For a reversible two-state process, no significant intermediates. We'll come back to that in a second. That's the conversation about a Van Hoff enthalpy versus a calorimetric enthalpy. And the overall enthalpy at any given, at that point, is therefore the enthalpy at the melting point. At this point, the equilibrium is, it is at equilibrium, and you can write down that delta G is equal to 0, and then you can solve for the entropy. You're already getting the enthalpy of at the melting temperature from the measurement you're making. But across the entire transition, there's potentially a change in the enthalpy, a change in the heat capacity. And so there's a temperature dependence to this entire process. If you go slow enough at every temperature, you're at equilibrium, but you're at different places in the equilibrium where there's more native and then less denatured. And then you go through the peak, and then on the other side, it's more denatured and more native. And so you basically have to treat this as a full titration where things are changing across the curve. And the enthalpy is changing and the entropy is changing, and you sort of have to take all of that into account. In principle, again, if you're going slow enough, there's nothing complicated going on. Sometimes there are irreversible events that happen when you melt stuff. Proteins don't always like being melted. But in any event, these simple expressions that we've already used a lot will apply, okay? And so this is part of sort of the complexity of differential scanning calorimetry. You sort of have to have some picture of what's going on and how you're going to account for it. Okay, now, in fact, we can define this because the enthalpy as a state function is just native minus denatured. And we can define this as a difference. And then we can relate this to some kind of an equilibrium. Okay, and describe this as the enthalpy difference between the denatured and the native, going from the native to the denatured. So this is written in that way. That's why denatured is on the top and native is on the bottom. And you end up doing things like integrating over the space and getting some relationship that you can then equate to the Van Hoft relationship. So we won't go through all of this completely, but you can see here that if you differentiate this expression, this was at the very end of the Van Hoft section, they derived this equation to show you that there was a temperature dependent heat capacity. Sorry, these are all offset here. They're supposed to mean temperature dependence on the same line. There's a temperature dependent heat capacity, temperature dependent Van Hofts, and you get these kinds of relationships as though it's a two-state process. But the calorimeter is not necessarily assuming that, it's just measuring whatever it measures. And if there's more than a two-state, if there are stable intermediates, high concentrations of intermediates, complicated pathways, et cetera, that will show up. Okay. And so the end point, the thing that you really need to know about that is simply that the Van Hoft enthalpy and the calorimetric enthalpy, is that summarized here? That's summarized up. It's here where I use that expression. The book uses this expression for what the overall calorimetric enthalpy is. If they're identical, equal to 1, then the transition is two-state and easy to interpret. If they're not identical, which is often the case, then you know things are more complicated. Okay, and so that's as much as you sort of need to know about that at the moment. So, as I say, calorimetric DSC experiments are typically used for protein melting. That's sort of what they're used for, or real phase changes that we are doing measurements that have to do with proteins that'll actually phase change. Analogous to what happens when you make a Cajal body. Sometimes you actually do chemistry. So the chapter, this section ends with an A plus B to C. Maybe there's a ligand binding to a protein, or maybe it's two proteins interacting. You can do this by this calorimetric technique. It becomes complicated because not only do you have the reaction, you also have melting. And so the ligand and the protein will melt, the complex will melt, And what you're doing across this entire process is looking at the heat of ligand formation, ligand binding to protein or protein binding to protein. So at every temperature, you have this equilibrium going on. Maybe you're actually now breaking them apart and denaturing them. So the interpretation of this becomes complicated. Generally speaking, people don't do this by DSC. They tend to do this by a titration method called isothermal titration calorimetry. And the reason for that is that it's simpler to interpret the data. You're not doubling up measuring reactions and melting, okay? What you're doing is you're titrating something into a device. It can be sort of a lollipop design, a cell design, where you have a high concentration of a ligand, for example, outside, but it's held at the same temperature. And then you titrate in small steps into the cell. And when you do that, you get an evolution of some amount of heat. Okay. And that heat is the heat of binding or the heat of rearrangement, whatever is happening. Okay. So if it's ligand binding to a protein, then there's a simple binary reaction. It's making a complex, and the heat is dependent on the enthalpy of that reaction. Okay. Now, in titration experiments like this, the amount of heat depends upon the enthalpy, but it also depends upon the amount of reaction that is occurring, the number of moles of complex that are being formed. So the number of moles of complex then depends upon the volume of the sample and the concentrations of all of the reactants. And so the interpretation of calorimetry data is usually very precise in terms of how big is the volume, because it's literally going to give you the heat from that volume, how much stuff is in there on a weight basis, on a mole basis, and how much reaction has occurred. And so you need to know all of that stuff, the volume times the concentration, then times the enthalpy, to be able to interpret what's going on. And so the experiment is done as depicted here. You push a little bit in, you measure the heat. You push a little more, you measure the heat. You push a little more, you push a little more, you push a little more. And you design this in a way that you get a full titration curve. What this is depicting is the fact that as you make more and more complex, there's less and less reaction. And so the heat disappears because there's no reaction. Okay, now for a simple reaction, P plus L, ligand going to a complex, we can show, okay, that's what it says in the text, that the amount of ligand formed has something to do with the total amount of protein, excuse me, the amount of complex formed, fully ligated protein is the total times this quotient, which involves an equilibrium constant and a concentration, that should be a sub A, and a concentration of ligand. And so this basically shows you a way of going about how you derive this. I think on the next slide, I actually show you how this is derived. And I'm not going to go through all of that because I'm showing it to you. Go up. Okay, so if you take the total concentration as the free and as the complex, and then you can rearrange everything in terms of this heat and this complex concentration, but you can solve for this in terms of P total times this equilibrium. If you look at this, this is basically a hyperbolic. This looks like a binding curve for oxygen binding to hemoglobin, for example. We'll be deriving that again next week, I think. So in principle, this type of a titration can give you the enthalpy and a binding constant. That's something that's really difficult to get out of a DSC experiment, but this is the whole point of ITC. It can be determined not from a single injection, but from the differences between injections over many injections. And as you measure those heats over many injections, you can actually go in and solve this for the total enthalpy and the total equilibrium constant, okay? So if you know the ratio of the total ligand to protein, which you define as R, the IDC data can then be plotted as a function of R. That's that derivation that you're going to go through on your own. Okay. And you can fit that binding curve shown here. So here's a titration curve where you get a certain amount of reaction, but then it diminishes with time. And if you plot that amount of heat versus the ratio, you can then fit this curve in terms of an equilibrium constant and in terms of an enthalpy. Okay. This is showing basically what the steps involve. It's essentially a quadratic solution that you end up solving for. And you can end up getting this titration solution in that way. And so this is showing a more complete or more precise titration. This one just is bigger steps. When you do this, you have to design this very carefully. How much protein do you have? How much ligand are you going to inject? How much heat is going to involve? And can you go through a full binding titration going from 0 bound or 10% bound to 90% bound during those titrations? How much volume do you have in the syringe? What size injections are you going to make, etc.? It all sort of has to work out precisely. And so this is done a little more finely here, where you get this nice titration curve. How much reaction are you making? And then it diminishes and you can get a value for K out of it. Remember, this is being done at one temperature. If you repeat this at different temperatures, then you can plot the enthalpy versus the temperature, and you can get the temperature dependence of the enthalpy out of this. And this is an important parameter. It gives you that information that I told you is assumed in the Van Hoff analysis. Okay. The figure on the right here is showing you a situation where the affinity is really tight. When the affinity is really tight, all the ligand that you add binds, and you get a complete reaction with however much ligand you add. You never get a diminishing curve. It all binds, it all binds, it all binds. And once you've saturated all the sites, there's nothing left. And so you get a curve that sort of looks like this. Each step gives you an estimate of the enthalpy, but you can't really get a K out of this because it's not a gradual curve that you can use the methodology in the preceding slides to solve. So this type of reaction is impossible, quote unquote. Down below, we're going to talk about how you can do this, but you basically have to be in a region where you have a reasonable amount of heat and you can step across the titration curve and get it. Okay. So that's basically summarized here, what I just said, that the limit is that the K can't be too big. And these tight reactions, all of the reaction occurs. And so you go from reaction to there's nothing left. Okay. So you can't fit it this way, but you can use something that involves a competition. This is the equation that's derived in this box. And the competition is if you put some other kind of weak binding ligand already into the site, and then you titrate with something that binds tightly, it's basically a displacement reaction. And when you displace the reaction, there's this competition that allows you to get the sum of two reactions. You're competing something off, and you see both of those reactions occurring simultaneously. So you essentially have the sum of two heats, and you get what looks like a normal titration curve. You already basically have to know what this equilibrium constant is, and then you can back out from that an apparent binding constant. And that's what's shown in this figure here, where it derives an apparent binding constant in terms of the pepstatin binding constant and the unknown. Okay, so you can get this by some kind of a competition technique. Competition techniques are real common in lots of different methodology to get at hard to measure numbers. So in the homework, I ask you to derive this, and the derivation is analogous to this, except it involves two competing reactions. Okay, so you'll figure that out. Okay, you know what the final form looks like. You know what the original titration curve alone looks like when you combine them. Okay, so this transition at the end of this chapter, as I said, was added to this version of the book to introduce some methodology and to show that the Van Hoff plot, which is sort of a theoretical sort of a thing, it was shown in the data here, in the figure here in the chapter, now compares Van Hoff analysis with something that we're getting from calorimetry analysis, okay? And you can make this additional equation, equating of these two values and learn something about the complexity of a reaction. It's often true that for complex reactions, things are more complicated than they seem. So for example, I just edited, I'm in the process of editing a paper, meaning somebody has submitted it to a journal, where not only can you get equilibrium information out of this, you can actually get kinetic information, because the shape of that injection assumes that the entire mixing occurs and the reaction occurs quickly. And it may not. There may be an evolution where it ejects over some time, and then it mixes at some time, and it reacts over some time. So you can extract other kinds of stuff out of this if the reaction is slow, if there are intermediates, if there's more complexity, et cetera. So the things can be a lot more complicated. But for the simple mathematics, if the Van Hoff and the calorimetric are the same, and the enthalpies are the same, it's a two-state reaction that may have no temperature dependence to the enthalpy. In the case where you have temperature dependence, this curve will be curved and it'll be much more complicated. Okay, so let's bury that. Let's bury that. So let's now go on, and I think this is where we are. So this is the start of the next lecture, which involves, in some ways, a repetition of some of what we've done, but going into more depth. And we're going to do this a couple of times where we go into more depth. Okay, and I don't have the other thing opened up. Let's go open up that chapter. So I think that other chapter is this one. Maybe I'm wrong. No, it's not that one. It's this one. Yeah, this is the one that we may need if we need to go back to the chapter to discuss something. So let's get that out of the way and let's open this up. Okay. So this is a chapter that there have been multiple versions of this book. I think along the way, there have been like 5 different versions of this book. Okay. And each version mixes stuff up in a slightly different way. I was actually just looking at the version that I have on my desk here, and it has a completely different version of a chapter that I could have used. Okay, so this chapter says something that is often said at the beginnings of books like this. I was reading a different book about this introduction, a book by Tanford, and it kind of says exactly the same stuff. Early on in the development of molecular biology, we usually describe it as the development of molecular biology. It was sort of really the development of biochemistry and biophysics and molecular biology. Early on, we didn't understand stuff. We didn't know what proteins were. We didn't know what macromolecules were. We sort of thought that these solutions of macromolecular things were not really true solutions. They didn't really have freezing point depression. They were actually slowly diffusing mixtures of things that we called in those days colloids. Okay. Colloids in those days were thought to be weird mixtures of amino acids and other factors. We literally didn't know that a protein was a linear sequence of amino acids that folded up, okay, into a certain tertiary structure. And so back in those days, there was a lot of confusion about this. And this is going all the way back to the 20s. And there's a couple of books that have been written, one more recently than the other, that sort of says this, kind of deals with the fact that a lot of people thought that the thermodynamic concepts that really evolved from the work that Gibbs did in the late 1800s didn't apply to macromolecular solutions. It didn't apply to life. We basically thought that life, cells, organisms didn't obey the laws of thermodynamics. We thought that there was some violation of the laws. In the 20s, a scientist by the name of Svedberg developed something called the analytical ultracentrifuge, which we'll be talking about soon. And he discovered that proteins are not just large, they sediment very quickly. They're also homogeneous. They're not colloidal. They're not suspensions. They're not mixtures of things. They really have a homogeneous character. They're a single entity that sediments quickly. This was essentially the discovery of a single chain, the discovery of a tertiary structure. It was applied to things like myoglobin and hemoglobin in the early days. The hemoglobin data demonstrated that you could also have multiple chains that made a single thing, and that then discovered the whole idea of quaternary structure. So this was a kind of a bridge between this idea that no, they're just colloids, okay, which actually Svedberg was studying at the time, to this transition to unique tertiary quaternary structure, okay? And so once that occurred, we began to appreciate that we could use the laws of thermodynamics and the principles that came out of the mathematics that we have evolved here so far, and we're not by any means done, could apply to biological specimens and biological samples. I don't say it here usually. I think I say it in medical biochemistry. Why do we introduce thermodynamics and med biochemistry is sort of the slide. If you went back and looked at those slides, I may try to find that the next time just to show it to you. The idea is that thermodynamics allows you to study what happens. This is now a restatement of the first law. Maybe I say that down below. Maybe I've added that down below. But basically it involves, allows the discussion of where does the work and the heat go? And how do we transition from one kind of an energy to another kind of an energy? Okay, and so that's the value of things like thermodynamics, that it allows you to do that. Okay, and it allows you to understand what's happening in biochemical reactions. They make the point that we have sort of already made, but we will make it again and again, and it's down below here. Can you see that cursor as clearly as, well, oh, this is not showing up. Here we go. Thermodynamics depends upon a very large number of molecules. The origin of this is something known as statistical mechanics. Statistical mechanics, sorry, my writing is a little sloppy there. And that basically depends on a large number of molecules. And he simply makes the point, a very pertinent point here, that in a low concentration of virus, 0.01 mg per mil, which is actually pretty concentrated for virus, if it's 100 million molecular weight virus, if you do the math here, and compare this to the number of molecules, the number of particles corrected for Avogadro's number, this is something like 6 × 10⁻⁻ particles per mil. Okay, that's a big number. Okay, that's a big number. And so statistical mechanics, statistical thermodynamics, therefore is safely applied in stuff like this. Okay, that's the point that they're making there. Okay. So we then make the point that we have to define certain concepts. One of the concepts is a component. So generally speaking, in biochemistry, in the test tube, in the lab, we're talking about a solution that is a single phase containing sometimes more than one component, but we need to define what a component is. And a component is basically an independent variable chemical substance. What that really means is I can add a component to a solution and I can account for it. I can use it in some kind of reaction and I can say, this is the concentration of this component. Even when that reaction produces many species. So the example that they give is hemoglobin and oxygen. If you make a solution of hemoglobin and oxygen, the solution at the very least contains water. This is not going to let me write. Contains water, hemoglobin, and oxygen. But then there's a reaction that occurs, and we can have hemoglobin with 1, 2, 3, or 4 oxygens bound. There's still only one component, though. There's hemoglobin that is in reaction with the component oxygen in the solvent water, and we're ignoring the fact that the solvent probably has a buffer at a particular pH. So at equilibrium, there are 3 independent components. Okay, 3 independent components. Now, what we want to do, therefore, is define the state of the system. And the stuff that we've been deriving involves state functions, okay? Enthalpy, entropy, free energy. So to define the state of the system, we have to be able to specify how much hemoglobin, how much oxygen, and then in addition, what the temperature and the pressure are. And if we can specify this stuff, then we know that we will get back to the same equilibrium state or state of the system, okay? Now, mathematically, one of the ways of talking about this is to assume that you had some pressure, temperature, and numbers of moles or amounts of 3 components, okay? And then you can write down what is called a total differential. So I'm writing this down as a serum, a mixture of hemoglobin and oxygen. Serum will generally have lots more stuff, but let's break it down to its sort of essential stuff that we care about. I can write down the total differential of the serum in terms of the 3 components or multiple components. And so I can write this down as the partial of S with respect to P at constant T. And I really need to add here N sub I not equal, or N sub J not equal to I later, okay, dP. And then, oh no, that actually constant N sub I. That probably only needs to be N sub I. And then the partial of S with respect to T dt, and then the sum over a partial derivative with respect to S, partial N sub I dni at constant temperature, pressure, and N sub J not equal to I. This is where I really needed to do that. Okay, and so you can see that I can write down this total derivative in terms of whatever the variables are that I'm telling you apply to that system, okay? Now at constant pressure, and constant temperature, these values are going to go to 0, and I'll only be talking about variations in the N. But this is a general thing that I can write down. Okay. For example, in the cases that we've already done, we went through internal energy, E, we talked about enthalpy, we talked about free energy. If you go back and look, I don't expect this to be in your heads, although it should be eventually. The internal energy depends upon the entropy and the volume. So we could write down a total derivative in terms of dE ds constant V ds plus dE dV constant S dV. This would be the total derivative of dE for these two parameters. In that previous derivation, we ended up with the equation dE is equal to T ds minus P dV. So necessarily, this derivative is equal to T, and this derivative is equal to P minus P. Okay, so we can write down the total derivative, and then we can actually solve very often for what that total derivative is equal to. So we could do the same thing for the enthalpy. The enthalpy, it turns out, is a function of S and P. And we can write it down in the same sort of manner where it's dH, ds, ds, and dH, dP, dP. But we already then showed that these first derivatives correspond to T and V. And this is what we used, I think it was in table 1, to look at the dE and the dH. And then in the table 2, we derived free energy in terms of pressure and temperature. This is the one that we really cared about. This is the Gibbs free energy because we can control pressure and temperature. And again, we would get something that looks like dG, dV, dP, sorry, constant V, and dG, dt, constant P. And those we showed were equal to V and minus S. Okay, and so these are the equivalent total derivatives and what they're equal to. All right. And so that's sort of the value of knowing that these are total derivatives. These also lead to something else. So here are those equations written down a little differently. So this is off the web, I found this. So this is the equivalent of internal energy. We use E, physicists often use U. There's the enthalpy, there's the Gibbs free energy. This is the textbook that I skipped over, was A for Helmholtz free energy, and this was its equivalent equation. We didn't go over it. These are the natural variables, so you can end up writing this down as the partial of U with respect to S and the partial of U with respect to V, and this is the equation you get. Maxwell's relationships tell you that the second derivatives are equal to one another, and that's what this column over here refers to. In other words, the partial of T with respect to V at constant S will be equal to, excuse me, it's the partial, yes, and then the partial of P, it's actually partial of minus P with respect to S at constant V are equal to one another, okay?
Right.
Yes.
In this case, S is 0 or?
No, in this case, I'm sorry, that's confusing. This S in this case is entropy.
Okay, thank you.
Okay. The second derivatives are equal to one another. The importance of this is that, remember, these are all state functions. These are all state functions that are path independent. And so if you do a transition, and let's do it, well, let's do it here, it doesn't matter. U1 to U2. If you first vary the entropy and then vary the volume going to the end state, you will get the same result if you vary the volume and then vary the entropy. the path that you take doesn't matter. You will end up with the same delta U. That is equivalent to saying the first derivative, the first derivative and then a second derivative, these end up being written as the second derivative with respect to S and V in this way will be equivalent to V and S. Okay, so the path doesn't matter. Okay, I'll come back to that again. I just wanted to point out, because this is sort of another review basically of your calculus and of your differentiation and of some processes that we have to go through to get what's going on here. So this is a revisiting of doing the first derivative to get the slope and the second derivative to get the curvature. This is a similar sort of mathematical manipulation. I'll have more to say about this as sort of review soon. All right. So these two chapters that we're now covering, the one we've just covered and the one we're now starting to cover, are beginning to use the same language. So we already said that there are state functions that depend upon different kinds of variables, and that these variables can be extensive or intensive, okay? And we've already talked a little about extensive and intensive properties. What we want to do now is be a little more quantitative about this. If we have an extensive property like a volume that depends upon the amount of material, you can express this as moles or mass, okay? How do we deal with these properties? Specifically, if we have different components that we mix in some ratio, and the components have some volume, so imagine that we're mixing liquids. What's the volume of the final mixture? And how do we determine it? Is there a way that we can be quantitative about it? And so this leads to the definition of something called partial molar and partial specific volume. The definition given in the text is that any extensive property like volume can be expressed as a partial molar by taking the derivative of that parameter with respect to the number of moles, n sub I, at constant temperature, constant pressure, constant number of other moles in solution, and this will give you a partial molar quantity. Now, in the book, they tend to write this with a bar over the top. I was having trouble finding a bar over the top of these parameters, so I'll sort of mix this a little bit, but you should recognize that this is the equivalent of having a bar. Partial specific volume means per gram, not per mole. So this in the book is written down as a lowercase x. Again, it's written with a bar over the top. Okay, and it's the change in the parameter with respect to the number of grams at constant temperature, pressure, and the number of grams of other components, J not equal to I. Okay, so it defines here these subscripts mean hold temperature, pressure, and all the other components constant. Okay. Notice that the distinction here that we're making is what a total derivative is, dx dg, and a partial derivative. A partial derivative necessarily specifies some other stuff be held constant, okay? The total derivative doesn't necessarily do that. All right, and that's what we were doing in the previous couple of slides with the total differential. All right, the point of this is that we've now turned this parameter into an intensive property. It's no longer extensive. It no longer depends upon the quantity because it's the change in a solution when you add a small amount of this substance, either moles or grams. And so they then go on to make this more explicit, and they use volume as an example. And they just consider volume as a partial molar quantity, capital V, or a partial specific quantity. In the book, it might use that notation. I tend to use a partial specific volume. We often call it V bar. That's the notation, but it often has sort of a Greek sort of shape to it. I'm having trouble finding all of these symbols. But the notation is that it's the change in volume, the partial with respect of volume with respect to the number of moles, or the change in volume with respect to the grams, partial molar, partial specific. And notice these are equated to one, can be equated to one another, because if you divide this quantity by the molecular weight, you get the partial specific. Okay, so volume is extensive. Partial molar, partial specific are intensive properties. All right. They are not dependent on the size. All right. Now, what's the point of doing this? The point of doing this is that the V bar depends on the composition. That's why this is maintained and is specified at a particular pressure and temperature. It does not depend upon the amount. But the advantage of this is that question that I asked a little while ago, if you made a mixture of certain things, what would the volume be at the end? And volumes added up do not necessarily give you the sum of the total volume. You really need to sum the partial specific volumes times the number of grams, and that quantity can actually give you what the total volume is, because this partial specific volume accounts for the presence of the other components. It accounts for the fact that I change the volume when I add a small amount, and I know how much I change the volume because I'm defined by the composition that I'm in. So this nomenclature works down here for that very reason. Now, what the book does is it sort of derives this, okay? And it makes this logical. And what it says is, imagine we're going to build a solution. Okay? And so it goes through the procedure. And this is a standard way that textbooks do this. Imagine you're going to make up a solution with infinitesimal increments of n components. So we're going to have n components, but we're always going to add them in the correct proportion, the proportion that corresponds to the final mixture. And so I'm going to add a little bit of component 1 and a little bit of component 2 and a little bit of component I. And I'm going to keep adding a small amount. How small an amount? Well, I'm going to define it as d lambda, where d lambda is some kind of a small number. And so I'm going to add a small amount, and I'm just going to keep adding it in the right proportion so that it's the right proportion for the final. Now, what's the volume change when I do this? Well, the volume change will be the V bar for component 1. Remember, it's defined in terms of the total composition that we're making, times the dG1, number of grams, plus the V bar of component 2, times the dG2 plus the V bar component I times dGi. And then I'm going to make a substitution in terms of the dGs, that for this. And so I'm going to make this V bar 1 G1 d lambda, V bar 2 G2 d lambda, etc. And then I'm going to pull out all of the V bar 1 G1s because they're all constants. And I'm going to integrate from 0 to 1 because lambda goes from none added to 1, where 1 means what the final composition or the final volume actually is. And what's left behind is this sum. And the sum is the sum over Gi V bar I. okay, from component 1 to component n. There are n components. So this is basically a derivation in the logic in the fact that these partial specific, partial molar quantities allow you to determine things like the total volume. Okay, so in general, any total extensive quantity is the sum of the partial specific quantities times the number of grams. And so this is a general way of writing down that same equation. We just wrote down on that previous page, if I bother to repeat it, where's V is the sum G sub I, V bar I, okay? It's all,
Dr. Correa,
yep.
so where did that d lambda go? I think I missed that when you said it. V equals to, yeah.
So
you
the what is the integral? Okay, so that's a good question. Thank you. Okay, that's a good question because it's an integration. When you integrate d lambda, the integral of d lambda is equal to lambda calculated between 0 and 1. Okay, I should have done this. What that means is 1 minus 0.
Okay.
Okay, so the derivative of lambda, is simply d lambda. So if you have a function that's called lambda, then df ends up being d lambda. It's lambda, how do I write this? It's lambda to the first power. So the derivative is 1 times lambda to the 0th power. Okay.
Yeah.
D lambda. All right. And then you calculate it at the limits. Plug 1 into lambda, 0 into lambda, and that's obviously equal to 1. So it ends up being here as a 1.
Okay. Yeah. Thank you.
Okay. All right. And you can do the same thing for partial molar quantities. So we introduce this with volume because it's a nice way, generally, and with volume, any extensive parameter. Okay. But what we really want to do is apply this to some other quantities that become more useful. The partial molar free energy can also be calculated. It's the partial of G with respect to N, constant temperature, pressure, number of moles. We give it a special symbol called mu. And we do this because we want to understand something about multi-component equilibria. Okay, so this is the definition. And then just like up above, the total free energy can be called the chemical potential. And it's the sum of the number of moles times the partial molar volume, just like we did up above. Okay, and so it's this sum then adds up to give the total free energy. All right. Now, going back to the idea of a total differential, all right, when we write down a total differential for G, I showed up above, it was the partial of G with respect to T dt, partial of G with respect to P dP. Now we're talking about components. That wasn't in the Maxwell's relations slide up above. It also involves a number of components. So it's the sum over the partial of G with respect to N dN. Okay, and so as we showed in previous slides, this is minus S dt, V dP, plus the sum over the chemical potential of I dNi. Okay, and so this is sort of where we're going here because this is the quantity that we're interested in using. So at constant temperature pressure, dt goes to 0, dP goes to 0, and all we're left with is this. Delta G is the sum mu sub I dNi. Okay? However, up above, we've already defined G as N sub I mu sub I. All All right. And so when we take the derivative of this, it's the derivative of a product is 1 times the derivative plus the other times the derivative. It's the first term times the derivative of the second plus the second times the derivative of the first. Okay. And so dg is also equal to this. This term, notice, is right here. If this is dg and this is dg, the only way that this can be true is if this quantity right here is equal to 0. So what that implies is that the change in the chemical potentials across multiple species are not independent and can be expressed in terms of all of the others. All right, and they begin by then applying this to a simple case down below. Imagine a 2-phase system, all right? Phase alpha and phase beta, okay? And these are in equilibrium with one another at constant temperature pressure, so those derivatives fall away. Using this equation up above, this means that the change in free energy is equal to the chemical potential of this component in phase alpha times dni in phase alpha plus the chemical potential of I in phase beta times dni beta. Okay, and then they use this thought experiment. Imagine that you transfer a little bit of component I from the alpha phase to the beta phase. When you do that, I guess the way they're doing this is from the beta phase to the alpha phase. We're losing a little bit of it on the beta. We're gaining a little bit of it on the alpha. This is one of the odd languages that we use in thermodynamics. An infinitesimal amount transfers such that we're still always at equilibrium, and therefore the free energy is 0. Consequently, we can equate these two terms to one another and then combine them and bring them to the same side. So the dn alpha can be plugged in and we can combine them. And so we have mu sub I on alpha and minus mu sub I on beta. The minus sign came from this equality, okay, is equal to 0. The amount that we exchanged is arbitrarily small, but arbitrary. So the only way that this is true is if mu sub I alpha must equal mu sub I beta. For a system to be at equilibrium, the chemical potentials must be at equilibrium. Okay. So this is beginning to apply these partial molar, partial specific quantities to equilibrium processes. This is the partial molar free energy, what we're calling chemical potential. And we're defining what equilibrium is. Equilibrium means the chemical potential is constant across this membrane. Okay, so that's a definition of equilibrium, constant chemical potential. Chemical potential will become what we call a driving force. Now, membrane potentials are an okay place to apply this. We'll come back to this, I think, near the end. But a more general and useful thing is to imagine some kind of equilibrium. You have A moles of A and B moles of B reacting to make G moles of G and H moles of H. Okay. We can write this down as chemical potential of A and B and G and H, where the A, B, C, H's, A, B, G, H are stoichiometries for the reactions. Consequently, using what we've described above, the chemical potential times A, the stoichiometry for the reaction, plus the chemical potential of B times its stoichiometry, must all add up to give the same free energy on the right side or on the product side. G times mu G plus H times mu H. So for this system to be at equilibrium, every time you react a little A, you have to divide essentially by the stoichiometry to account for the change in B divided by its stoichiometry. If this is 1 to 1, then they're just all equivalent. If it's 2 to 3, then you have to account for the fact that 2 molecules react with 3 molecules to make these all equivalent. Okay, and so this reflects the small changes that are going on in the reaction. And notice, if you react A and B, you make G and H, and so they have opposite signs. You're losing some of this, you're gaining some of this. It's the opposite sign. You're gaining some of this, you're losing some of this. We're writing this as left to right, but you can imagine it going both ways. Now we can write down the total derivative of this in terms of mu sub A, dNA, mu sub B, dNB, etc., across all of the changes that are going on here. But now we're going to plug in equilibrium and divide by the terms here. And as I'm looking at this, I'm saying to myself, there's something not quite right there. It's here. When I make that substitution, so there's a sign problem here. This negative sign should get plugged in here so that you can bring these to opposite sides. So if we have negative signs on the right side here, so I think, I may be wrong about this, but I think all of these should have this negative sign here, reflecting this negative sign. And then when you set it equal to 0, because we're at equilibrium, then you can.
Dr. Correa, is
Yeah.
it when, because the equation like 2.21, when you move all the term in the right side to the left side, it should be changed the sign and it's equal to 0, is that right?
Yes.
Okay.
Right. So these are all equal. And so what we're doing is we're multiplying by an equal quantity going down here. Okay, so we're multiplying this whole equation by something that is the same value, dNA over A. And we multiply that times the first term, but we'll multiply the second term by dNB over B and et cetera all the way across. These are all the same value, so we're simply multiplying by the same value all the way across. That's why this should be a negative sign. I think that's a mistake in the book. And then when you do this, the A's cancel, the B's cancel, the G's cancel, the H's cancel, and you end up with AU, A, and no, then you up with UA DNA plus B DNB, U sub B, excuse me. A times its chemical potential plus B times its chemical potential. And then you can bring these to the other side with the sign is G times its chemical potential times H times its chemical potential, okay? This is what defines equilibrium, that all of the chemical potentials of the reactants, correcting for the stoichiometry, wait. You can cancel all the term according to 21. So I've got written this down wrong. What have I got here? Yeah, I wrote this down wrong. Let's go back to the math. This is what happens when I try to reproduce a book and I get caught up in the mu A dNA, mu B dNB, mu G dNG. from 21. Huh. Does that look wrong to you too? The A's cancel. This should be, I started talking about this as though I knew what I'm talking about here, but I think that's also a mistake. Wow. I hadn't noticed that when I did this. Does this not end up being U sub A dNA plus mu sub B dNB? Because it's the coefficients that cancel. Mu sub G dNG plus mu sub H dNH. Double check that yourselves and come back to that. We're going to go on from here because this becomes simplified at this point later on. Where are we? At equilibrium, chemical potentials are mixtures are linked to their concentrations. So this is what the text does. And so now we want to know how the mu sub i's depend upon their concentrations. Now that's this equation up here. I've actually reproduced this line right here. Oh, these all cancel because of this equation. So okay, I'm getting myself confused. These all cancel, sorry. These all cancel. Where's my pen? Come back. Hello. These all cancel because they're equal. And that's what gives us this equation. Don't think of that. I'm missing the whole point here. Yes, these are equal, so these can all be taken out and multiplied. I've kind of done this backwards. These can be all taken out, and that's what's left behind. That's how you get to where I just went. It's equal to 0, and this can cancel. Okay. Sorry. You go through all the trouble of reproducing it, and then you don't pay attention. So let's go ahead. So this sum, the stoichiometry times UA plus stoichiometry times UB must be equal to stoichiometry times UG, stoichiometry times chemical potential of H. We now know that all of these chemical potentials are linked to one another. They're all dependent upon the concentrations. And so the question is, how do they depend upon the concentrations? So to discuss this, we have to discuss the concepts of ideality and non-ideality. So first we start with ideality. Ideal solutions traditionally obey what's called Raoult's law, where the vapor pressure of each component is proportional to its mole fraction. Okay, so it usually can be expressed as something like this times its mole fraction. Okay, where this is the pressure, vapor pressure of the pure substance. Okay, and so ideality in general, we don't really want to work in mole fraction. We'll get rid of it when we can, or we'll use it when it's a convenient. But it's a convenient way to start. The enthalpy of mixing is 0. We've already said this about we've already said this up above about the internal energy. The mixtures, the components don't interact, and so mixing them doesn't lead to any interaction. So the enthalpy of mixing gives you 0. The entropy is purely statistical in the way that we've been making sort of mixtures. How do you combine various things? Let's count the ways. Let's put things into boxes. Let's put things into grids. And the equation that we derived previously was that delta S of mixing is minus R sum over N sub I ln X sub I. So this was sort of the statistical nature of it. So if there's no interactions and it's statistical mixing, the free energy of mixing is the enthalpy minus T delta S. The enthalpy is 0. So this is the free energy of mixing. Now, the free energy of mixing can also be written down by final minus initial. Okay, so the solution minus the pure components, a sum over all components. Okay, so when we do that, then we can go back to this idea of a chemical potential as written down previously here. And we can write this down as the sum N sub I mu sub I summed over all components, where it's using this relationship, the partial of G with respect to N sub I, remember where this is coming from, times N sub I summed over all terms, okay, minus the same sum, but over the mixture, over the pure components. The mu sub I 0 is pure, okay? So we can combine these in terms of N sub I's, take the sum N sub I out and multiply times the difference, and we get U sub I minus mu 0 sub I. But that must equal what we just said on this side over here. Okay, so it must equal this. So this expression is one way of writing the free energy change down. This expression is another way of writing the free energy down in a statistical concept where we're using mole fraction. The mixture that we have, the N sub I's, are completely arbitrary. They're just some mathematical term. Some mathematical term. And so how much of N sub I that we are using is arbitrary. They could be anything we want them to be. Therefore, they can cancel here because they were chosen independently and we can just ignore them. This equation must be true for each component independent of one another. Consequently, mu sub I minus mu sub I 0 must be equal to RT ln X sub I. Okay, so this is a way of writing down how mu sub I depends upon concentration in mole fraction terms. The standard state or reference state corresponds to pure components. So if X equals 1, then ln1 equals 0. And therefore, if that were true, then the mu sub I is equal to the standard state chemical potential. Mole fraction, as I've already said, is not really convenient for biochemistry. So we can convert arbitrarily to any weight we want, weight or any concentration unit we want. We can absorb whatever the factor is to make that math. How does this become mgs per mil? Or how does this become molar? Okay, and we could use that unit. In this case, it's grams per liter. The arbitrariness of that conversion ends up going into the standard state. In this case, standard state makes sense if C sub I is 1. In that case, this term goes to 0 and mu sub I is equal to mu sub I standard state. Okay, and so this will obviously change with anything and everything that we use. Okay, and so this is another way of expressing chemical potential. Now, transitioning to non-ideality, and this was one of the things that you did in that first problem set out of the review book, the mathematical computations. We could add an activity coefficient here. In mgs per mil, this book is using Y for activity coefficient. Okay, so in general, Y sub I will depend upon everything else in the solution, temperature, pressure, solute concentrations, etc. But it will go to 1. It will be ideal when the total concentration becomes dilute. So as total concentration goes to 0, the activity coefficient will go to 1. And the equation will convert back to this simple ideal expression. Okay. Now, we're going to do some math here that is going to confuse you. Okay. I'm going to do my best to explain where it comes from. Okay. It is just convenient to talk about this stuff in terms of standard states and change standard states and change units in various different units, mole fractions, concentrations in terms of weight or molar, etc. So we can write the same expression down, this expression here, in terms of mole fraction, where we also introduce an activity coefficient. We're now going to call it F, okay? And what we want to do is we want to talk about our, the way the transition occurs in the book is they say, these are the macromolecules, okay? These are the solutes that we're talking about here. The I's refer to solutes. The component 1 refers to the solvent. And so we could write an expression down for the solvent in exactly the same way. Mu sub I1 is equal to mu sub I mu1 standard state in terms of its mole fraction times its activity coefficient. So you already know mole fractions. The sum over all mole fractions is 1 because there's one total amount. You know, it's the number of moles of I over the total number of moles. Okay, so the sum ends up being 1. So the mole fraction of 1, the mole fraction of solvent, excuse me, is equal to 1 minus the contribution from the solute. Imagine you only had 2 components. So we could substitute in here for x1 in terms of 1 minus x2. So we can now take the natural logarithm of x1 and make it the natural logarithm of 1 minus x2. Those are identical. But then we want to express this as some kind of a Taylor expansion. And what a Taylor expansion is a polynomial that looks like the logarithm. If you were to plot logarithm of 1 minus x2 as a function of x2, it would have a certain shape. And what you want in a Taylor expansion is to derive an equation that looks like that logarithm function, okay? I am trying to convince you that this is true by suggesting that you plug in numbers. Assume that x2 is 0.01. That means 1 minus that is 0.99. The natural logarithm of 0.99 is 0.01, which is minus x2. So the first term is approximately already equal to whatever x2 is, okay? If you add more and more terms, it gets closer and closer. That's one way of convincing yourself that this is okay, all right? There's a video on that website that I just sent to you that describes Taylor expansions that you might find useful if you want to look at it. So the chemical potential of solute minus its standard state can be written as minus RTX2. We're now going to plug this into this equation and neglect higher order terms momentarily. And when we take the logarithm of x1 times f1, the f1, the logarithm of product is the sum of the logs. So we'll have this ideality, non-ideality term or activity coefficient term here, okay? So for dilute solutions, convince yourself of this as best you can. The mole fraction can be written down in terms of a different concentration scale, weight concentration, and we can make that substitution. Notice we're going from RTX2. We're going to go now to RTC2 with some correction terms, okay? These correction terms will shortly disappear, all right, as we absorb them into certain factors, and then there'll still be this non-ideality term. So we can do the same thing with the non-ideality term, the activity coefficient. We can express it in terms of some kind of a Taylor expansion. If non-ideality was a approaching 1 as C2 goes to 0, It will generally be less than 1. Okay, so we can write this down in terms of a power law, in terms of concentration, where we have these arbitrary placeholders, alpha and beta times C2 squared, C3 squared. The first term falls away for the reasons that are explained in that PowerPoint or in that video. And so then this becomes this first term involving, notice, there's an RT term in front of both of these. So the RT term comes out, okay? And then the V10 term comes out, but we account for it in terms of the coefficient inside. So the B now also has this V10 term. The V10 is essentially the volume of pure solvent, okay? And we can then express this as the expansion term that we described up above in terms of X2, which has now become C2. We've carried in this change in units involving a molecular weight. And then we've added the non-ideality term in terms of the concentration of the solute squared times some coefficient, which we're going to call a virial coefficient. At low concentrations, the product BC2 is approximately equal to 0. And so this term will reduce to mu1 minus standard state chemical potential is equal to this minus RTC2, and then it's divided by this M2. The chemical potential of the solvent is reduced by the addition of solutes. That whole derivation is to allow us to plot this. And that is shown in an equation down below. Let me go to that equation because I want to describe it. The chemical potential of the solvent is reduced as you add solutes. If it's ideal, it's a straight line. That equation is a straight line equation. If it's non-ideal, then it will deviate from a straight line, and the deviation will depend upon the magnitude of the non-ideality. The non-ideality, which started as an activity coefficient and has now been defined as a virial coefficient, will dictate the curvature. It'll curve down, more non-ideal, or it will curve up, less non-ideal. Okay, it depends. All right, so I'll come back to that in a moment. Okay, so this is the general form of the equation. It involves 1 over the molecular weight, which we call the first virial coefficient. It involves the second virial coefficient, which we sort of plucked out of thin air using the activity coefficient derivation. We're going to come back to what that means now. Okay. Now, what we talk about are macromolecules, and what we're interested in is macromolecules. When we do the statistical mixing problem up above, wherever we did that, implicit in that mixing was the fact that it was small molecules that looked like solvent and they occupied the same volume. Remember, the definition involved no volume, no interactions. Now macromolecules have volume and they're charged, okay? And so they contribute non-ideality in lots of ways. They occupy lots of space that displaces the solvent, okay? And so the macromolecule conformation, or some picture of the macromolecule, becomes a starting point for discussing this. So if the macromolecule was globular down here, that's the typical thing that you're talking about. Everything you're doing with John involves crystal structures of globular proteins. We typically envision that they're spheres or some kind of ellipsoids, and they occupy some kind of compact space. Alternatively, they could be random coils. In other words, denatured proteins or some kind of a polymer, or maybe a polysaccharide or nucleic acids. They have this sort of expanded shape because they basically are doing a three-dimensional walk with each step, with each new residue, for example, and they occupy some larger volume, which is often defined as a radius of gyration. The radius of gyration generally depends upon how many linkers, and that gives you some idea of how big they are. And so we need to think about this, either the compact structure or the random coil, in terms of the volume of solution occupied. This is often described as what we call excluded volume. Other molecules can't go into it. They could have spherical symmetry if they're random coils. They've randomly expanded, so you can think of it as a Gaussian distribution of segments, or they could be a compact shape. Alternatively, you could have things that are rods. So you can imagine double-stranded DNA, some kind of a coiled-coiled transition, some kind of a structure that has a long length and a short diameter. Okay, so that's depicted in this figure from the book. Here's random coils, here's compact. Spheres are what we typically think of. In the history of this field, we tended to think of prolates or footballs, or oblates, which is sort of discs, or you could have rods, okay, with a particular length and a diameter, which you can't see in this dark version. Okay, so we're now going to talk about this non-ideality in terms of this shape, okay, but we're now going to revisit everything that we just assumed. Okay, the first thing we assumed is that they have a delta H of mixing that is 0. That's no longer going to be true. The heat of mixing corresponds to favorable solvent-solute interactions. That's where the chemical potential of the solvent varying comes from. Okay, I'm going to go back to that figure in a second. So the solute is going to be affected. The chemical potential is going to be changed by the solvent is going to be changed by the solute. So this will give what is called a positive value of B. They're interacting with one another. If the solute-solute interactions are stronger, then the virial coefficient might be negative. In other words, it might interact with itself, or it might be repelled from the solute. It might have a phase change. It might precipitate. It might simply associate into a complex of some kind. Okay, we'll revisit this later. Large excluded volume is something that we can quantify through some mathematics. The quantification involves what is that excluded volume. So U here, unfortunately, that's a U. It looks like a chemical potential. It's not meant to be. It's meant to be a U times Avogadro's number divided by molecular weight squared. Okay, this is the general equation for what the volume is. Okay, this is for a structure that is uncharged at the moment. So this general equation for excluded volume, this general equation for a virial coefficient, I said that wrong. This is a general equation for a virial coefficient, and it has to do with the excluded volume corrected for the molecular weight. That's the correct way to say what I just didn't say. All right. For a compact sphere, this can be approximated by something involving the molecular weight, the partial specific volume corrected for Avogadro's number. If you plug this into this equation, this is what you get. You get something that's 4 V bar over M2. If it's a rod, this is the volume, excluded volume of a rod. If you plug it into this equation, this is what you get for the second virial coefficient. Depends on the length over the diameter times V bar over the molecular weight. Okay, there are other equations for random coils that I will only momentarily discuss. So we've already discussed this in terms of van der Waals contacts. Okay, and we think of van der Waals contacts as the volume occupied and closest approach. But when you have macromolecules, you have to sort of expand this. This little sphere is basically a macromolecule, many molecular weight. Okay, their closest approach is center to center distance. Okay, that becomes a different way of defining excluded volume. That excluded volume basically is this bigger volume because when they touch one another, it's really the closest that this center can get to the other molecule. Okay, there may be other kinds of attractive interactions between molecules that account for this. There may be repulsive interactions that make this actually bigger than it appears. But at a van der Waals contact level, this is the excluded volume. It's this center to center distance. And so this bigger circle becomes the excluded volume. Okay, and so that's what those equations represent. All right, so here's that plot again. Chemical potential of the solvent is a function of the concentration of the solute. In ideal solution, it's just a straight line. If it's non-ideal, it curves down because B is bigger than 0. If B is attractive to itself, then it actually curves up a little bit. If it's too attracted to itself, then it may actually phase change. Okay, and so these are the general depictions of what you might get in a general cartoon for the chemical potential of the solute, the solvent in terms of the solute. Okay. This is that discussion that I'm not going to go through. This is describing what you do with random coils and some other concepts that I won't emphasize right now. So the expression that we have up above involves a chemical potential in terms of a unit involving molecular weight, and then there's some other term there, and that other term involves a virial coefficient times the concentration. If you multiplied through by molecular weight, you could rewrite that equation. So there's a molecular weight in the front. You can take this molecular weight term out. And when you do that, you have to add a molecular weight all the way through. So if you multiplied and divide by molecular weight, you would get this term that involves a molecular weight internally. And so you basically have a correction factor. If a solution is ideal, how much will B vary depending upon the protein concentration? It says up above, I think, that the product goes to 0 at low concentrations. And so this table is derived for 5 mg per mil. Okay. And so spheres will tend to have a B value of 3 times 10 to the minus 5. Remember what this is up above? It's 4 V bar divided by M. Okay, so if you plug in a typical V bar for a protein, which is around 0.72, and a molecular weight for a typical protein, this is the order of magnitude that you will get for B times concentration corrected for this molecular weight term. And what you will get is a correction factor of about 1.5% deviation from ideal. That's for spheres. The reason we care about shape is that rods will have a much bigger virial coefficient. If the length on D is 100, really long rod, it will tumble in solution and occupy a huge amount of space. All right. So it will give a bigger number. You can plug these values into those equations and approximate these numbers. It will give a number that's at 37% deviated from ideality. That's a huge deviation from ideality. Random coils will give you something around 25%. This theta solution will be essentially virial coefficient is 0, and it will be an ideal solution. That's a definition. Okay. So this whole section is giving you some context for what is an ideal solution, what is a non-ideal solution, what order of magnitude the virial coefficient is, and how much it deviates from ideality. Okay, now we want to then go on. We're going to run out of time here pretty quickly. We want to go on to circumstances where we can take some of this stuff into account. What is the value of some of these kinds of measurements? Because sometimes in biology, we deal with things that are semi-permeable membranes, and we want to know how to define the equilibrium across the membrane. We already did that up above in example 1. But experimentally, we might do what is called dialysis or some kind of filtration method for purification. And there will be some thought experiment or calculation that goes into what the equilibrium is across this membrane. Or we could set up an experiment. We have a ligand on one side and a protein on the other side, and we can study the ligand binding to the protein and conclude something about that interaction. We can actually use this technique to measure the molecular weight. Notice molecular weight appeared in these reactions up above, or in these equations up above. And so the technique of osmotic pressure, which was one of the first methods used for determining molecular weight, okay, can give you this kind of information. Down below, we'll talk about what we mean by passive and active. So if you have an equilibrium across this membrane, we generally will have a cutoff for dialysis of something like 10,000 molecular weight. There'll be different phases, and the criteria as we set up above will be that the chemical potentials are equal to one another. Okay, so we can imagine hemoglobin on one side and oxygen and salt being the other components. So the idea is that we have one component on both sides in equilibrium with a solute, a macromolecule. And we're going to assume chemical potential defines equilibrium. However, we just went through a couple of steps very quickly, showing that the presence of the macromolecule lowered the chemical potential of the solute. So if you have macromolecule on one side, the chemical potential of the solvent is necessarily not equal to the chemical potential of the pure solvent. Okay, so due to the presence of solute, these two numbers cannot be equal to one another. In other words, we can't ever have equilibrium with this simple idea. Something else has to change. What is it that has to change? The book goes through this sort of thought experiment telling you that maybe we could change the temperature, but it turns out experimentally that what we really do is we change the pressure. The pressure changes on one side. This is the origin of osmotic pressure. So we leave the one side, it's pure solvent, at normal 1 atmosphere pressure, and we increase the pressure on the other side by some amount. It's represented here by the symbol that is, I think, meant to be pi. Okay, so it's the chemical potential, the change in the free energy with pressure at constant temperature. Up above, if you go looking at those state functions, you will find that this is the volume. Those state functions and those derivatives have use. Okay, they're not just mathematical games. They actually give you a parameter, the volume. Okay, so if we actually then take the derivative of not the free energy, but the chemical potential with respect to pressure, this is essentially a double derivative. That's why I went through that step. Then you get the partial specific volume. Okay, so the chemical potential of the solute is equal to its standard state plus this parameter that we evolved involving the first and second virial coefficient plus a pressure difference. And the pressure difference is the derivative of V1 dP integrated from P0 to P0 plus pi, the osmotic pressure. Okay, and this should probably be written as a V bar here. Okay, I've written it here on the side. What they sort of do in the derivation is assume that this V bar of solvent is approximately the same as the V bar of pure solvent to simplify the derivation. Okay, so when you differentiate this, when you integrate this, you get V10 times P evaluated at P0 to P0 plus pi. So you get V bar 10 times P0 plus pi minus P0. So you get V10 pi. That's what you get right here. Okay. So that's a little reminder for integration. This assumes that the volume is not dependent on the pressure. So this is what the result is. Okay. And if we rearrange and we make the assumption that the chemical potential is not that different under dilute conditions from pure solvent, then this is when we can bring this to the other side. We can get rid of this sign and equate them. And we end up with this equality, okay, where the osmotic pressure is equal to RT. Actually, this cancels out. Sorry. This should cancel out here and here when we bring them to the other side. And so you get this RT, two terms, the ideal term and the non-ideal term. If the solution is dilute, then the BC term is close to zero. It's not B is zero. The BC term is approximately zero. Then the osmotic pressure is equal to RT concentration divided by M2, the molecular weight. So this is the equation that shows that osmotic pressure is a measure of molecular weight. Okay, and this is what was used early on, literally in the 1920s, to measure molecular weights of macromolecules. And so we're going to stop with this slide, I think. We're going to stop with this slide. So at a real concentration where we have non-ideality, this is the equation we're going to get. Okay, and what you'll notice has happened here is we've brought C to the other side. So we now simply have, and the RT is multiplied by both terms. So RT is now on both terms. So this quotient, osmotic pressure divided by weight concentration, is equal to RTC over M plus BRT over times C. So the intercept gives you the molecular weight. The slope gives you information about the virial coefficient. In this particular example, this is native aldolase and denatured aldolase. It's denatured in 6 molar guanidine down here. So it's 1 over the molecular weight. So the aldolase is a complex, and the intercept tells you it's a bigger molecular weight than the subunits. The slope tells you that the virial coefficient for the native protein is smaller than the virial coefficient for the denatured aldolase. Guanidine makes it denature. And so now it looks like a random coil. It looks bigger. And so it has a bigger slope because the virial coefficient is big. And then the table simply shows you the apparent molecular weights of various proteins done by osmotic pressure. You can see hemoglobin here at 66,000. That's a tetramer. You can see the aldolase itself. You can see it looks like a tetramer as well because the subunits are 42,000. So multiply by 4 and you get something close to 156,000. And then other kinds of substances, all right? And so osmotic pressure can be used to get molecular weight, but it also can be used to get information about the virial coefficient. And notice what we're getting out of this. We're getting information about the shape. It's globular because it has a smaller, more compact structure in the native state. It's expanded because it's denatured in the guanidine denatured state. Okay, so we're getting multiple pieces of information out of this experiment. We're getting something about size. We're getting something about non-ideality. We're getting something about shape. Okay. Okay, so where we go from here is getting introduced to charge and charge effects. This will now be called the Donnan effect, and that's where we're going next. Okay, I'm going to stop sharing this because it gets into, okay. So it will only be a few slides when we go ahead. Okay, so sorry about that little messiness. So you must have a lot of questions that you're going to hesitate asking. There is a problem set out there. We're not quite done. So the problem set that's out there is for the stuff we just finished through calorimetry. There'll be a problem set for this, but you can delay starting that until we finish, because one of the questions will involve charge effects or the Donnan effect. It involves measuring the non-ideality due to excluded volume and charge. So that will come next week at the beginning of lecture. I'm going to be regrading some of the stuff you've turned in, or grading whatever you've turned into me to kind of get everything up to pace. That probably won't happen until next class. Do we have any other questions at this point? Or do we need anything at this point? Your next, go ahead.
I have a question regarding homework 5. So are we taking this week to work on homework 5? I mean, I'm still stuck on a few questions. I mean,
Well, homework 5 was
Will
from
be-
the end of the lecture we just finished.
okay, yeah.
It included the calorimetry stuff.
Yeah, yeah.
Because it
doesn't-
included deriving that equation in the box.
Okay,
Now,
okay.
homework 6, which I don't think maybe is posted, will be questions from this chapter. So
Okay.
homework 6, if you look at the end of this chapter, you will see questions. Number 7 involves estimate B and 1 plus BMC. So it's asking you to calculate virial coefficients and deviation from ideality. And that's the stuff that we're going to get to the
Okay.
beginning of next week. So homework 6, which I think is not posted.
Mm,
I think it's not posted. It's in the on the website on Canvas. It's the very next block, but I don't think I put the assignment in there yet.
You have not. You have not.
Yeah, I was gonna add another question that has to do with exact differentials.
Okay.
Do we have any other questions?
Mm,
Okay, so next time, what is in that block is, I think it says chapter 15. It's some introduction to binding. It's some introduction to ligand binding to a protein, or protein-protein interactions, and how we analyze protein-protein interactions or ligand-protein interactions, how we analyze data. Eventually, we'll actually derive oxygen binding to hemoglobin. We'll derive the equation for Monod-Weyman-Changeau cooperative interactions. Given how quickly I go through stuff, we probably won't get through all of that by the end of next week. It'll spill into the following week. And then there'll be a problem set from that chapter as well. So the deviation in the old flow of this course is, I usually get to methods after I get through thermodynamics and I get through the binding experiments, okay, that we're going to be going through next week. So that next block, that next folder. The little section that we just did on calorimetry was an introduction to methods and how you use methods to extract some of this information. Okay, to extract the molecular weight, to extract the virial coefficient, to extract an extent of non-ideality. How do you go about that? Because the way that this is developed is all this theoretical stuff. Here's what thermodynamics is good for. Here's what state functions are good for. Here's how you can think about all of these parameters, but so what? Well, I want to know molecular weights. I want to know something about shapes. I want to know something about how they interact. I want to know something about how they bind. I want to know how they bind it with what free energy they bind. I want to know what their enthalpies are. I want to know what their entropies are. So we're beginning to look to kind of stack together techniques that will give you that information. Once we finish the binding stuff, so that will that'll take 2 weeks. We'll then start doing more methods, and we'll select various chapters to do that. But at the same time, I'll have you start reading papers that apply these methods, and I'll apply them to particular circumstances. I tend to use other people's papers. Next week, when we go into this, I'll introduce a paper that talks about the sign of the enthalpy and the sign of the entropy, and what weak forces give you those signs and magnitudes. The sum of how many hydrogen bonds, how many van der Waals contacts, how many electrostatic interactions, and then what the sign of it is. Is it repulsive? Is it retractive? How does it contribute to enthalpy? So we'll look at a paper that measures that and then apply it to the chapter that we're going to be talking about. I think we'll talk about that paper probably in the middle. I might probably mix it in and do it in the middle, because the chapter itself does it too. And then we'll start talking about methods, specific methods, and apply specific papers as well that use those methods to study different kinds of biological chemistry or biochemical interactions. How far we get and what we get to depends a little bit on how long it takes me to do stuff. You can see, even when I mess up, I like to go through all the steps, and I like to make sure we walk through all the steps so that you can follow along. You may not always like doing that yourself, but I'm trying to encourage you to do that yourself so you can derive this stuff yourself, and you can see sort of behind the curtain where this stuff is coming from. And so how far we get and how many topics we cover, how many methods we cover, will depend a lot on how quickly I go. The syllabus suggests where we're going to go, but that's going to be modified depending on how long it takes us. So we'll get to more conversation about that in the next couple of weeks. Do we have any questions at all? Okay, so in the same vein, the assignments are meant to sort of make this practical for you, bring your math skills up so that later on you can understand some of the things that we're going to be doing. And it becomes easier for you to understand what we're doing and how we process and analyze data. Do we have any questions at all? Any comments at all? All right, so I'm going to stop the recording.